on uncertainty quantification and calibration. So I'm the session chair, Daniel Andrade from Hiroshima University, and let's welcome our first speaker, Yusuf. He's presenting is the volume of a Credal set a good measure for epistemic uncertainty, and it's joint work with Michele Caprio and Eyke Hüllermeier. Okay, thank you. Perfect.
So, first of all, thank you for the introduction. My name is Yusuf. In the US, you would say Sale, maybe. And I'm quite happy to present a joint work with Michele Caprio and Eyke Hüllermeier on the question whether the volume of a Credal set is a good measure for epistemic uncertainty. First of all, since we have a broad audience, I think at UAI, it is called Uncertainty in AI, but we have a broad audience, I would like to spend some time on motivating this quite specific but important question on the volume operator, whether it's a good measure for epistemic uncertainty or not. First of all, you know that nowadays uncertainty, reliability, trustworthiness, it's like very, very prominent keywords in machine learning research, especially for those of you working in health sectors or, you know, socio-technical systems. And on this first slide, I mean, we have predictions by EfficientNet on test images from ImageNet. On the left-hand side, our neural network predicts with very high certainty, I would say, that this is a typewriter keyboard. And on the right figure, we see that the neural network predicts that this is a stone wall with an even higher certainty. And I think everyone in this room would agree that we don't see a typewriter keyboard and we don't see any stone wall here. Otherwise, please, let's take this discussion to the offline sessions. And okay, hence we have this lack of uncertainty awareness in machine learning systems, hence we should care about uncertainty in machine learning. When we speak about uncertainty in machine learning research, usually researchers, scholars distinguish between two types of uncertainty. The first of both types of uncertainty, called aleatoric uncertainty, refers to the notion of randomness, that is the variability in the outcome, which is due to inherently random effects, and it's a property of a data generating process, and as such, irreducible. Imagine, I don't have a coin here, but I'm tossing an imaginary coin, fair coin. Even we know that the coin is fair in statistical terms. We know it's a Bernoulli distribution with a parameter of 1/2, and the probability for the positive class, hence heads, is 1/2, and for tails is also 1/2. We don't know the actual outcome of our next coin flip. And the second kind of uncertainty is called epistemic uncertainty. And this is mainly caused by lack of knowledge, hence from the Greek word, and refers to the epistemic state of the agent. When we speak about an agent in this talk, we will speak about the learning algorithm itself. And since this is concerned about the epistemic state of the agent, it is principally, well, we can principally reduce epistemic uncertainty on the basis, for example, of additional information. For example, additional data we see in our learning process. Hence, we have aleatoric and epistemic uncertainty, which will be abbreviated as AU and EU. So, on this slide, first of all, what we see are probability simplex and barycentric coordinates. But the key takeaway is every point on this on each probability simplex corresponds to one specific probability distribution on the label space Y. On the far left, we see a hard label prediction. Hence, given our features, we predict one specific hard label. Hence, in this case, it's A. By doing so with our learning algorithm, this specific predictor is not aleatoric uncertainty aware, also not epistemic uncertainty aware. In the middle figure, we see, I mean, this is very well known, probabilistic prediction, for example, a logistic regression, a neural network, and so far and so on, which is capable of outputting a probability distribution on a label space. Hence, in this case, we will have a specific probability for the classes A, B, and C. Imagine 0.5, 0.3, and 0.2. And by doing so, we are aleatoric uncertainty aware. But the important question is now, what about epistemic uncertainty? Hence, can we rely this probabilistic prediction, or what is the uncertainty of the machine learning algorithm about its probabilistic prediction itself? This, by this idea, we come to our far right picture. This is called a Credal prediction, and having input of some from mapping from a feature space to the space of all Credal sets. In a moment, I will also introduce formally what a Credal set is, but for the moment, you can consider the output of such an Credal prediction algorithm as a set of plausible probability distributions on the label space. Hence, not like in the case of B, we are not saying, okay, you should, hence you, the agent, should predict one specific probability distribution and somehow saying, oh, there is no epistemic uncertainty at all. We say, if you are, you, the agent, uncertain about your prediction, then give me a set of plausible probability distributions on the label space. And as you can see by the green ticks, this kind of learner predictor is aleatoric uncertainty aware, also epistemic uncertainty aware. Since we are in a machine learning context, usually one is interested in, okay, given such an uncertainty representation in terms of Credal set, hence when we have an output as a set of plausible probability distributions, how can we quantify aleatoric and epistemic uncertainty in the sense of, because usually in downstream tasks, you need one specific number saying aleatoric uncertainty high, low, epistemic uncertainty high, low. And we, this leads to the motivation also of our paper. In this paper, we focus on the epistemic uncertainty and ask us the question, is the volume of a Credal set a good measure for epistemic uncertainty? Okay, then let's come to the formal definition of a Credal set. A Credal set, first of all, let y and sigma y, where sigma y is just a sigma algebra, be a generic measurable space, and we denote by py the set of all probability measures on this given measurable space. Then we call a convex subset calligraphic P a Credal set. So far, so good. And let me also introduce two related notions from the field of imprecise probabilities, which is the following. Again, let y denote a finite label space. And we have labels y1 to yd, where d is a natural number bigger than 2. And we call p bar, which is defined as the supremum over our Credal sets, an upper probability associated with a Credal set, should be quite intuitive. And in a similar fashion, we call P underbar of A, where A is now sigma algebra, defined as the infimum overall or Credal set, the lower probability respectively. So now to our question in this paper, because as we've seen before also in this illustration, when I talked about the barycentric coordinates and the Credal set, hence we have a very specific geometric representation. Intuitively, it makes quite sense to say, why are we not taking just the volume of such a Credal set as a measure of epistemic uncertainty? Because imagine two extreme cases. In the one extreme case, the learner is very certain about its prediction. Hence, it will predict a set consisting of just one probability measure, and the volume of this will be zero, and zero epistemic uncertainty. And in the other extreme case, imagine the learner is fully uncertain about its prediction and will give us back the whole probability simplex itself, giving us full volume. What we prove in our paper is that in the binary case, that the volume of our Credal set satisfies some desirable axioms, which is also justified by many scholars in the uncertainty literature. And specifically in the binary case, it fulfills non-negativity and boundedness, quite intuitive to desire such properties. Hence, the volume of a Credal set is bigger than zero for all possible Credal sets, bigger or equal to zero. Hence, it's bounded. There exists such a real number, such that for all Credal sets, the volume is somehow bounded. The second property is continuity. We want that the volume is a continuous functional. The third property is monotonicity. Hence, if we have two Credal sets, Q and calligraphic P, and Q is a subset of P. In our illustrations, imagine our Q is a subset of this red Credal set I've shown you before, and somehow reflecting less epistemic uncertainty, then we require that the volume is smaller or equal to the volume of P. The fourth property we show is so-called probabilistic consistency, relating to these notions I've introduced you before with upper and lower probabilities. We say if the volume of the Credal set, or the volume of a Credal set P reduces to zero, if the distance between its upper probability and lower probability goes to zero for all A in our sigma algebra. The fifth axiom is a technical one. It's subadditivity, and for this axiom, we suppose that our Y is given as Y1 times Y2, and P is a joint Credal set on this Y space, such that P prime is a marginal Credal set on Y1, and P double prime is a marginal Credal set on Y2, respectively. Then what we desire and show is that the volume of P on this big space Y is smaller or equal, hence subadditive, to the volume of P prime plus to the volume of P double prime. The sixth axiom says, okay, if P prime and P double prime are independent, and I'm not going to technical details, this independence notion refers to independence notion of Credal sets. Then we say A5, hence subadditivity holds with equality, giving us additivity. Our last axiom is invariance. We say, okay, volume is invariant to rotation. Translation also makes it very suitable as a measure for epistemic uncertainty in the binary case. Let's further proceed. Now we've seen somehow quite promising results in the binary case, and also due to the fact that in the binary case, everything becomes quite simple. Imagine the simplex, the probability simplex in the binary case is just a line segment. And everything becomes quite simple. We can prove all these nice properties. Now our investigations leads us to the question, What happens if we have more than 2 classes in such a classification problem, hence a multi-class classification problem? First of all, let me just shortly introduce you some preliminaries. For a generic compact set K in Rd and a positive real number R, we call the R packing of K, which we denote by peg R, is a collection of sets K prime that satisfy the following properties. First of all, K prime is a subset of K, and the union of balls with radius R is a subset of K. And the elements of this set are pairwise disjoint. And the fourth property is a maximality property, which says there is no X prime in K such that properties 1 to 3 are satisfied by K prime with the union of X prime. And for you to imagine, this is just the packing number of K is telling us, okay, the cardinality of balls we can fit in a given space. We also require that, or for this picture, let's say P is a compact Credal set and Q is also a Credal set such that satisfies properties A, B, and C, where Q is a proper subset of P, hence Q prime is not empty. B, we require that P and Q are slightly different, but not too much. And for C, we have some also some technical condition. I will shortly skip over this to be in time and to somehow tell you something about this theorem. First of all, let Y be very general finite Polish space such that the cardinality of Y is D, and we fix a sigma algebra as the power set of Y. Then, if we pick any compact set P, hence a Credal set, and any set Q that satisfies these properties given by A to C, we say that the following holds. And here is a small typo. There is, forget about the prime and Q prime. What we say is that the normalized volume of P minus the volume of Q is bigger than the notion on the right-hand side. Hence, as you can see, for D going to infinity, the volume of P will concentrate in this orange boundary. Hence, making somehow the volume operator in higher dimensions not very suitable to quantify epistemic uncertainty. This is one of our results, and further results can be found in the paper. Let me quickly conclude. The key takeaways of our paper are representing uncertainty in terms of Credal sets is very appealing from a machine learning perspective. The volume is provable, a good measure of epistemic uncertainty in the binary classification case. But what we see is that in higher dimensions, it is not very effective. We point out some ways we can circumvent this problem, but finally, this will lead to some problems in higher dimensions. And maybe a future direction or question is, how feasible or efficient is actually a geometric approach to uncertainty quantification in machine learning? If you want to learn more about this, you can scan the QR code or come to a poster session. Forget about the blue bird. It's dead. It's X. But nevertheless, feel free to contact me and talk to me if you're interested in this. Thank you so much.
Great. Thank you very much for this interesting talk. Let's come to the discussion, which is by me. So let me first summarize my what I think is the goal and the main insights of this work, which is so the final goal is to get a measure of epistemic uncertainty by given a certain Credal set. So how can we get then reasonable measure of epistemic uncertainty. And this reasonable, this is formulated by certain axioms, which should hold. And the insights of this work are that for binary random variables, this intuitive notion of taking the volume of a Credal set as a reasonable, it is indeed a reasonable measure of epistemic uncertainty. And I compared like maybe to Bayesian statistics, the length of a credible interval. And but for more than two outcomes, there are problems. And so the first, what I would call like a degenerated Credal sets, if we come from an area and approximate only a line, then the volume becomes zero, but we don't want that the epistemic uncertainty is zero. And the second is the robustness in the robustness about a small specification. For example, the prior specifications, it becomes more pronounced when the number of outcomes is large. And so my questions and remarks are, so how relevant are these problems 1 and 2 in practice if we want to use the volume? So in particular, a degenerated Credal set, normally we might not really want that this is an output of machine learning. So if we get a degenerated Credal set, that might point to a problem maybe of our machine learning algorithm, because how can we be sure that the probability is exact, say, for example, 0.1. And from a practical point of view, we might care actually more about a relative change in epistemic uncertainty rather than absolute values. So for example, in active learning, we have a set of samples. We estimate the epistemic uncertainty for each of this, and we take the one which has the greatest epistemic uncertainty. And so again, comparing to Bayesian statistics, we might be more interested in Bayes factors than the actual value of a marginal likelihood. And then maybe problems 1 and 2 are not so important. So what is your sure?
First of all, thank you for the very thoughtful and the very good questions. First of all, to the first question, question A, I would say that we formulated this in a very theoretical setting, such that we are not making any assumptions that, for example, here it is stated that how is it possible that the third class has, for example, a probability, specific probability of 0.1. We come from an epistemic viewpoint in the sense of we say, okay, we have so much epistemic uncertainty or knowledge about, for example, the third class, that we can somehow give this a specific probability. In practice, I also agree that this can be seen different, but our viewpoint was, first of all, from a theoretical point of view, and we tried to go from this epistemic uncertainty reasoning perspective. And the second question on the relative change in epistemic uncertainty, we also tried to somehow, in the setting of the volume, to see, okay, what is the relative change in epistemic uncertainty, but also as shown in this theorem, that we actually, in higher dimensions, due to this property of the volume concentrating at the boundary, we cannot compare it. But I also generally agree that apart from this volume perspective, this makes sense to also go for a measure which somehow measures the relative changes in epistemic uncertainty. Thank you.
Yes, thank you. So are there any other questions from the audience? So we have some time for questions. No questions from the audience here, so maybe online, I'm not sure. No online questions? Okay. Oh, okay.
Hello, thank you for the nice talk. So I had a question on general evaluation of epistemic uncertainty in practical settings, so in the classification case. So when you're not working with epistemic uncertainty, one thing you can straightforwardly do is, for example, compute the entropy, right, of the distribution at the output. So I'm wondering if you thought about or did any studies on how entropy itself as a, an expectation value changes with the size of the classes.
And actually, this is the perfect question one could ask, because our second paper, Lisa is going to present about, is about entropy as a measure of epistemic uncertainty.
Well, thank you. I'll take a look.
Thank you.